Hello everyone. In this video we're going to talk about Cartesian products of sets. And so the name Cartesian should evoke some image in your mind, probably of Cartesian coordinates. So you're familiar with that as like coordinates in the xy plane or maybe the xyz space as well. And we're going to see that in a way this is related to our idea of Cartesian products with sets. And so the idea with Cartesian products is that we're considering, again, two sets, A and B. And for whatever reason, in practical context, it would be very clear, but we want to consider elements of A and B at the same time with each other. And so specifically, we might be interested in ordered pairs of an element of A and then an element of B. And so if we want to consider the entire set of possible ordered pairs of elements of A and B, we then define this as A cross B. So this is the Cartesian product of A and B. So I'll define in just a minute. So A cross B is then equal to the set of ordered pairs A and B, such that A is in the set A and B is in the set B. Okay, simple enough. Why might this ever be useful? Well, if you think back to actually these pretty simple counting problems that you learned about in middle school or whenever, or I guess in green, we're all from Sycamore, it's green school. So something like if Alyssa has 3 jeans and 5 shirts, how many unique outfits can she make? There's more that goes into an outfit, obviously, than just a pair of jeans and a shirt. But let's just make it simple. So, you hear that question and you probably think immediately, oh, well, I do 3 times 5, that's 15, right? Easy, done. And you'd be right. But if we think about this a little bit, we can break down this question to saying, well, there's a set, I might call it J, and these would be, the elements of this would be each of Alyssa's pair of jeans. And then I could have another set S, which would be the set of her shirts. All right. Well, if I think about the unique outfits that could be made from this, what I'm really thinking about, or what the question wants me to think about, is the set of ordered pairs of jeans and shirts, right? And each of those ordered pairs corresponds to a unique outfit. And so the set of outfits then corresponds to this set that's J cross S, the Cartesian product of J and S, right? So this is essentially, if I wrote it specifically, it would be, the ordered pair would be a jean and shirt. Actually, let me just do that, actually. So it's a set of possible ordered pairs of a pair of jeans and a shirt. And this corresponds to the set of possible outfits. And so when you're trying to find the number of possible outfits, what you're really thinking about is, okay, what's the size of this set? So this is how we denote the size of the set. And this evidently should be the size of J times the size of S, which then gives us 15 from the statement of the problem. Okay, so that's great. But still, if this is not the type of thing you care about, which I don't blame you for, I don't care about it either, there are much more important applications of the Cartesian product. So for example, let's consider just some typical spaces that you would see. So at the top here, we have a number line, right? And then below that, we have this 2D space, the XY space. And then below that, we have this XYZ space, so it's 3D space. So this first space, we would identify with the real numbers, right? So we might write this fancy looking R. And this 2D plane, we have geometrical connotations in our mind with the 2D plane. But if you think about it, really what's happening is that you have one axis, right? Let's say the x-axis, and that's a real number line. And then adjoined along it, so that they both meet at 0, is another real number line. That's our y-axis. And then the elements of this 2D plane really just correspond to ordered pairs of these real numbers. And that idea you're actually very familiar with because you're used to thinking about points in this plane as basically corresponding to these coordinates. This point has x and y coordinates, right? So if I have, this x coordinate here, so let's call this x, and this y coordinate here, then I, find the right point here, and this point will have coordinates x, y. But that really, it's just an ordered pair of real numbers. And so we can just as well say that this 2D plane is the set R cross R, the Cartesian product of R with itself. And so, as mathematicians always do, they abuse notation and they see, oh, we have this idea of multiplication of sets. So if we have a set multiplied with itself through this Cartesian product, we can say that we're squaring it in a way. So we write this. Now, nobody calls this R squared. What we call it is R2. And I think that's a bit more revealing because the 2 is really saying how many dimensions there are. Right? So when you start doing, college math and just get more entrenched in this sort of mathematical language that people who do math use, you'll become normalized to the idea of calling this R2. It'll just be part of your everyday knowledge. So the 2D plane we call R2, and then with our 3D XYZ space, we see that it's very, very similar idea. We just have now 3 real lines all adjoined to each other at 0. And so again, we have all these geometrical ideas of, this 3D space, but equally we can view it as ordered triples of real numbers. And so we can write this as R cross R cross R. Well, what does that give us? Well, we define this as R3. So this is the 3-dimensional real space. Okay? And then we could do this, for increasing natural numbers. R4, R5, R6, so on and so on. And then arbitrarily, we would just have Rn, where n is some natural number. And then this gives us our n-dimensional real space. Okay, and we're going to investigate Rn quite a bit when we come to linear algebra, or at least it'll be our sort of model space. And the last thing I wanted to talk about was this interesting correspondence that we get. So if you consider the complex numbers, I think you're used to the idea of viewing the complex numbers as a plane. And so on one axis, we have the real axis, where all the real numbers lie. And the other axis, we have the imaginary axis, where all of the purely imaginary numbers are. So like I, 2i, I root 3, all of that stuff. And any complex number can be written as the sum of a real number and a purely imaginary number, right? So if I have a point in here, the complex number I call z, I can write this always as x plus iy. So x is the real part of z, and y is called the imaginary part of z. So y is a real number, but it's the real number that gets multiplied by I to form z. Okay. So in a similar way to adding vectors, so this tip-to-tail thing that you learned about in physics, a very similar thing happens in complex numbers, where starting from 0 here, well, first we can sort of draw a vector from 0 to z, and this sort of gives a representation for a complex number z. And what we can also see is that we could have a vector going from 0 to the real number x, and then a vector here going up with length y, and this corresponds to iy, and then adding tip to tail gives us x plus iy, which is z. So you can see that, you're familiar with this idea of these basis vectors, and you have like these two, independent vectors corresponding to components of a vector. And so it's not crazy to associate z, which is x plus iy, with, oh, I don't know why that happened, with xy, right? X would be the real part and y would be the imaginary part. But this is an ordered pair of real numbers. And so we can represent this in our space R2. So that would be this point here, which has an x coordinate of x and a y coordinate of y. And so we can make this very natural map between the complex numbers and R2 that serves as this sort of just natural identification, or what's the right word? Yeah, I'll just say identification between these two sets. So I might say, yeah, there's a natural correspondence between the complex numbers and R2. And that's something that can be very useful to use. Okay, so in the next video we'll talk about functions, and that will get us to a real good starting point for a bunch of other concepts in math. All right.